We're going to look to see how we can represent functions as power series. Let's look at the geometric power series. If we have a function f of x to be defined as 1 over 1 minus x, let's look at that function. Hopefully you can see that it closely resembles the sum of our geometric series. Remember, this was our geometric series where r was called our common ratio, and the sum was a over 1 minus r as long as r did not equal to 0 and the absolute value of r was less than 1. In other words, when a is equal to 1 and r is equal to x, a power representation for this function could be this power series. Think about that. Just kind of match it up. If 1 was a and x was r, then this function that we call centered at 0 is equal to this series. And again, if a was 1 and r was x, we would get this series, which you could expand out as this. And of course, if the absolute value of r is less than 1, then we have to put on the restriction that the absolute value of x is also less than 1. Let's look at some graphs. Here is the graph of f of x equal to 1 over 1 minus x between -1 and +1. So just looking at this part right here. This graph is the graph of the series of x to the nth power between -1 and +1. I think you can see they are pretty much the same. So that's what we're going to try to find out. Can we take other functions and represent them as power series? The good news is that this is really very easy. What we want to accomplish, function to be in the format of a over 1 minus r. So we can then write it as our series from n equals 0 to infinity of a times r to the nth power. So let's look at example 1. How could we get it into that correct format? Well, first of all, we need a minus sign. So we could write it as this, 1 over 1 minus -x squared. Well, that looks pretty good. Okay, so we could see that a is equal to 1. We have this one matches this one. This negative matches this negative. So the only thing we've got left is r must then be -x squared. And yes, that's all there is to it. So my function, which now is 1 over 1 minus -x squared, can be written as a power series from going 0 to infinity of a, which is 1, times r to the nth power. You could leave your answer like that, but it's probably a little bit better to take out this -1. So I'm going to write it like this. So this -1, which is that, is still raised to the nth power. And then we have x, and then I can multiply those exponents to the 2n. That would equal to this function as long as the absolute value of x squared is less than 1. Let's look at that graph. So this is in Desmos. The graph that's kind of in pinkish red is our function of 1 over 1 plus x squared, but I've restricted the domain between -1 and +1. And then the blue is our power series. So I'm going to start out the power series when n is equal to 0. You just, of course, have a horizontal line. But as n approaches infinity, I'm going all the way out to n is equal to 50. You can certainly see that this power series matches up to our function. So let's give example 2 a try. Well, it looks a little bit different, so we have to do some rearranging. So first of all, I would write this as 3 plus 2x. Now the key thing that you might look at is that this right here needs to be a 1. Okay, so we can take care of the negative pretty easily, but how could I make that 3 into a 1? Well, we could just divide every term by 3, which is a legal thing to do. So now I have f of x equals 5/3 over 1 minus 2x over 3. So just a little bit of rearranging of algebra. So now we're going to compare it to the format that we need. So I can see that a is 5/3 and r is, oops, I dropped a negative, is negative 2/3 x. So my series shall be a times r to the nth power. Again, you could leave your answer like that, or we could do some rearranging. Again, taking out maybe all of these constants. So how about, let's do this. N equals 0 to infinity of 5/3. Then we have negative 2/3 to the n, x to the n. That would be okay. You could take out the negative 1. You could do a lot of things. I'm just going to give you a lot of possibilities here. So we would have 5 times negative 2 to the n, x to the n. And then here, I could rewrite this as 3 to the n plus 1. Lots of different ways. Again, you could pull out the negative like we did over here. Do want to go back and say that this was perfectly fine as an answer. So again, just rewriting a function as a power series, and we call that being centered at 0, and that is because our absolute value of r is less than 1, and if we remove the absolute value, you can see that the middle of negative 1 and positive 1 is indeed 0. Let's look at number 3. That x cubed might present some problems. So you know what? Let's just pull it out in front and rewrite it like that. That's legal. So maybe I can do something with this. So I could rewrite this as 1 over 2 plus x. But remember, I need that to be a 1. So I could divide everything by 2. So I could say this is x cubed times 1/2 over 1 minus negative x over 2. Now that can be written as a power series. So I have x cubed times my power series of 0 to infinity of a, which is 1/2, times r to the nth power. And yes, that would be an acceptable answer. You could do some things with these x's if you wanted to join them up. So let's see if we could do that. And we could maybe join up the 2's and take out that negative 1. So let's see if we can do all of that. So I'm going to take negative 1, and that's still to the nth power. The 2's, 2 to the first and 2 to the nth, that would be 2 to the n plus 1 power. Then I would have x. I have x to the n times x cubed. X to the n times x cubed. What can I do with those exponents? I can add them. So that is an alternative way to write this, and I kind of like that. It looks nice. It looks neat. Once again, let's just compare the function to the power series. As the power series gets way out there, you can see how they do indeed match up, and you can really see how they match up between negative 2 and positive 2. Now look at example number 4. Well, that doesn't look anything like the other examples. Remember, we've got to get this into that format. That's just not happening. How can we take one fraction that looks like that and possibly make it into a fraction that looks like this? Partial fractions. Let's decompose this. So if I factor this, I could rewrite this as a over x minus 2 plus b over x plus 1 and solve for a and b like we did a few chapters back. So we would have 3 equals a times x plus 1 and b times x minus 2. So letting x equal to negative 1, I get b to be negative 1. And if x is positive 2, I get a to be positive 1. So my function could be written as a over x minus 2 plus b over x plus 1. Now those two fractions certainly could be in that format if they are not already. So I would have f of x equals to 1 over negative 2 plus x. Then, let's see, I could write this as negative 1 over 1 plus x. So this right here needs to be positive 1. So I need to divide everything by negative 2. And that's already positive 1. Just need to change that to a minus sign. So let's see, I have negative 1/2 over positive 1 minus x over 2. And then negative 1 over 1 minus negative x. So I can take my function and rewrite this as two power series added together. So for this power series, I have a times r to the nth power. Remember, I want that negative, and what's left is my r. So this is one of the first times r is positive. Then I'm going to add it to my second power series, where a is negative 1 times r to the nth power. So that is how you could rewrite our initial function as the summation of two power series. I encourage you to graph the given function and the power series. Might need to look up how to do that on Desmos and see how they do agree.